morning students. Chapter 7 Alternating Current. Yes, we have discussed in this chapter about AC voltage applied to a resistor, AC voltage applied to an inductor, AC voltage applied to a capacitor. Okay, now there is one important method in this chapter which is called phasor or phasor diagram, phasor method. So first question is, what is phasor? What is phasor? See, phasor means rotating vector. Rotating vector. Phasor is called rotating vector. Now vector, what is meaning of vector? See, we know that AC voltage, it is given by, for example, V is equal to Vm sin omega t, or we can say AC current, it is given by I is equal to Im sin omega t. For example, yes or no? Yes, it is. Okay, AC voltage is equal to Vm sin omega t, AC current I is equal to Im sin omega t. So yes, we can represent this voltage and current as a vector. Voltage and current, they are not vector quantities, but we can represent them as vector. Okay, we can represent V and I as vectors. Remember, V and I are not vector quantities. They are not vector quantities. We just represent them because why? Why? Because see, V is equal to Vm sin omega t. Value of voltage continuously changes with time. Value of current continuously changes with time. Yes or no? Yes, it is. Yes or no? Yes, it is. So yes, we can represent V and I as vector. So now, how to denote any vector? How to represent any vector? See, for example, x-axis, y-axis, it is origin. Okay, if I want to represent V is equal to Vm sin omega t as vector, then I have to draw one vector from origin having magnitude equal to, is equal to Vm and direction omega, angle that is omega t. Yes or no? V is equal to Vm sin omega t, so it is magnitude and it is direction. So yes, I have to draw one vector like this. Okay, it's this magnitude is Vm and this is omega t. Clear about this? Now see, omega t, time continuously changes. 0, 1, 2, 3, 4, 5, 6, dash, dash, dash. Yes or no? So this angle continuously changes. Okay, for example, if time increases, obviously omega t increases, and thus this vector rotates with angular speed omega. Vector rotates with angular speed omega, and such rotating vector is called phasor. Clear about this? So again, AC voltage, AC current, we can represent V and I as vector. V is equal to Vm sin omega t, magnitude, its amplitude, and its phase we can consider as direction. So yes, it is one vector, and this vector is rotating. Yes or no? Yes, it is not stationary. But this vector is rotating. Like this. Clear about this? So yes, vector rotates with angular speed omega, and such rotating vector is called phasor. Clear about this? Yes, if it is phasor of V, if it is phasor of V, then see, if I am taking its x component, okay, if I am taking its y component, then yes, x component will become V is equal to Vm cos omega t, and sin component will become V is equal to Vm sin omega t. Simple. Its x component will be x component will be V is equal to Vm cos omega t, while its y component will become V is equal to, it is Vn sin omega t. Clear about this? So it is about phasor. Why it is called rotating vector? Because omega t, that is phase, it is function of time and it continuously changes. Okay, as t increases, omega t also increases, angle increases, means this vector rotates, this vector rotates, this vector rotates. That's why it is called rotating vector, and this rotating vector is called phasor. Okay, now for purely resistive circuit, purely inductive circuit, and purely capacitive circuit, we will see phasor diagram. See, for pure resistive circuit. See, remember, for pure resistive circuit, phase of V and I are same, means phase difference between them is 0. Okay, V and I, they have same phase. V and I have same phase. Yes or no? Same phase, it means if phasor of V, it is in this direction, phasor of V, it is in this direction, then yes, phasor of I, it is also in this direction. Phasor of I is also in this direction. Clear about this? So yes, for pure resistive circuit, V and I, they have same phase. So yes, V is in this direction, then I is also in the same direction. Now as V rotates, I also rotates, because they have same phase. Because they have same phase. Second one is pure inductive circuit. Purely inductive circuit. Yes, in purely inductive circuit, what is relation? Yes, we know that I lags behind V by phase pi by 2. Yes, we know this relation. Okay, I lags behind V by phase pi by 2. So if it is phasor of V, lags behind, it means yes, phasor of I is in this direction. It is phasor of I, and yes, this angle is 90. This angle is 90. Clear about this? Okay, if this angle is 360, this angle will be 270. I lags behind V by phase pi by 2. By phase pi by 2. Clear about this? Okay? Okay. Third one, pure capacitive circuit. Pure capacitive circuit. See, in pure capacitive circuit, this statement is like this: I leads V by phase pi by 2. By phase pi by 2. Leads means is right. So if it is phasor of voltage, phasor of current, it is in this direction. It is phasor of current. This angle is 90. This angle is 90. See how to easy to remember. Pure resistive circuit, I and V, they both are in same direction. You have to remember just for pure inductive circuit. If phasor of V is in this direction, then phasor of I is vertically downward. In capacitive, it is opposite to inductance. It is opposite to inductive circuit. See difference between them. See difference between them. Clear about this? Clear about this? So yes, you have to remember such phasor diagrams. Clear about this? Okay. So yes, it is about phasor diagrams. Now see, next topic is LCR series AC circuit. Yes, we have discussed AC source connected with only resistor, then only capacitor, then only inductor. Now see, understand title. LCR series AC circuit means resistor, inductor and capacitor. These three electrical components, they are connected in series with AC source like this. Okay, they are connected with AC source like this. It is inductor having inductance L, capacitor having capacitance C, and resistor having resistance R. Connected with AC voltage having potential difference V is equal to Vm sine omega t. V is equal to Vm sine omega t. Clear about this? Okay. So yes. Here, inductor having inductance L. Okay, yes, pure inductor having inductance L, capacitor having capacitance C, and resistor having resistance R are connected across AC voltage V is equal to Vm sine omega t. V is equal to Vm sine omega t. Clear about this? So yes, here three components L, C and R, they are connected across AC voltage in series. That's why it is named LCR series AC circuit. LCR series AC circuit. Clear about this? Okay. Now see, yes, as these three components are connected in series, if we apply Kirchhoff's rule, then according to Kirchhoff's rule, okay, at time t, how to write this? Remember, in first theory, according to Kirchhoff's rule, V is equal to IR. Second, V is equal to L di upon dt. Third, V is equal to Q upon C. Here, as these three are connected in series connection, we know that for series connection, how to write equation? Yes, V is equal to IR plus L di upon dt plus Q by C. V is equal to IR plus L di upon dt plus it is Q by C. Clear about this? So yes, it is equation. Now, how to simplify this equation? See, here it is a term having I. Yes or no? Yes, it is. Here it is term having I, and here it is term having Q. I will convert this whole equation with respect to Q. We know that I is equal to dq upon dt. So therefore, di upon dt is equal to, it is d square q upon dt square. D square q upon dt square. Yes or no? Yes. So put values in this equation. V is equal to, it is Vm sine omega t. I, so as it is IR. So I you have to replace by, yes, I you have to replace by dq upon dt plus L. Di upon dt means it is d square q upon dt square plus q upon c as it is. Clear about this? Okay. Now I will divide this whole equation by L. So therefore, Vm upon L sine omega t is equal to R upon L dq upon dt plus d square q upon dt square plus q upon LC. Okay, so if I rearrange this equation, how to write? D square q upon dt square plus r upon L dq upon dt plus q upon LC is equal to Vm upon L sine omega t. Clear about this? And yes, it is called second order differential equation of charge. Second order differential equation of charge for LCR series AC circuit. For LCR series AC circuit. Clear about this? Yes. D square q upon dt square plus r upon L dq upon dt plus q upon LC is equal to Vm upon L sine omega t. It is called second order differential equation for charge. Yes, it is called second order differential equation for charge. Clear about this? Now, yes, it is one question, okay? Okay, yes, for LCR series AC circuit obtain second order differential equation of charge. So yes, you have to write this. Now we have to compare this equation. Remember, in case of forced oscillation, for forced oscillation, yes, remember 11, chapter number 14, oscillation, last theory, forced oscillation. What is the equation of forced oscillation? D square y upon dt square plus b upon m dy upon dt plus k upon m y is equal to f0 upon m sine omega t. Yes, it is second order differential equation for displacement. In case of forced oscillation, it is second order differential equation of displacement. So yes, second order differential equation of LCR series AC circuit and second order differential equation of displacement. See, they both equation, they have same form. So yes, now we will compare these both cases. That is for electronic and then it is for mechanics. Yes or no? How to compare? First comparison starts from, see, how to compare. This case, y displacement y. D square y upon dt square. Second order differential equation of displacement. D square q upon dt square. See, d square q upon dt square, dq upon dt and q. D square y upon dt square, dy upon dt, and it is y. So yes, it is second order differential equation of charge. So yes, here you have to compare with charge. Okay, we know that velocity v is equal to dy upon dt. So here current I is equal to dq upon dt. Clear about this? So yes, from first step, d square q upon dt square, d square y upon dt square, first comparison. dq upon dt, dy upon dt. R, that is resistance, and here B is damping constant, or you can say resistive constant. B. Here it is analogous to resistance R. Clear about this? Then inductance L, mass M, inductance. And remember this comparison we have done in chapter number 6. That is, mass is equivalent to inductance. Okay. Then Q, that is displacement y. L, that is mass M. So 1 upon C is K. Okay. So yes, force constant or damping constant K. Okay, it is reciprocal of capacitance, that is 1 upon C. That is 1 upon C. Any doubt? Any doubt? Yes. This Vm upon L sin omega t. This side is F0 sin omega t. So here it is periodic force. And here it is periodic voltage. Here it is periodic voltage. Clear about this? Okay, so yes, you have to remember such equations. You have to remember such equations. Okay, it is yes, it is comparison between mechanics and electronics. Clear about this? Okay, so yes, it is one IMP question. That is what is LCR series AC circuit. For today, this is it. Now, in next lecture, we will see solution of this equation. Solution of this equation. But for today, this is it.